Last lecture. So end of an era. We are talking about batteries today. Batteries, battery chargers. And this is a topic that we recently added to this class just because it's become so relevant. So it's become such a big part now of embedded systems, of designing electronic systems. And it's become such a big part of student senior projects that we decided gotta have it somewhere. We put it here in this electronics 2 class. So I'm not a chemist and I'm not an expert at chemistry and I don't understand a lot of battery chemistry. Battery chemistry is a very advanced topic. It is something that a lot of people spend their entire lives trying to make minor improvements to. And so I'm not going to talk too much about this because if I did, I'd be wrong. But I'm going to talk a little bit. So for the most part in this lecture, we are dealing with lithium ion battery technology. That's become the predominant technology for rechargeable systems. There's a variety of different flavors of lithium ion batteries, but they all have lithium ions as their primary charge carrier. And they operate on this principle of intercalation. And that is where it's a situation in which atoms or molecules can be trapped inside of a matrix of other atoms or molecules. And typically it's graphene, but there's lots of ways to form these matrices in which a atom or molecule can become trapped. And usually they become trapped through ionization or protonation. So they either gain or lose an electron or gain or lose, there's lots of ways to do it, but basically usually there's some sort of state change that happens that causes them to become trapped. Sometimes they're trapped. Again, this is, I definitely shouldn't go too much into, it's usually they either gain or lose a hydrogen or they gain or lose an electron. And in the case of lithium ion batteries, this is a reversible process. So these lithium ions can become trapped in a matrix, which is one of the terminals of the battery. And then it is possible through an electrochemical process of ionization and deionization that they can move in and out of this matrix. It's important to note that lithium is used a lot of different places. It's used in a lot of different battery technologies. So I just want to mention really quickly, there's a difference between lithium batteries. If you see these commercials like, Energizer Lithium, now the longest lasting battery for mobile, blah, 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 if something is referred to as a lithium battery, that's typically referring to a lithium anode battery. And that's different. That's sort of more, that's like a traditional battery just with a better anode. That's not the same as lithium ion batteries. Lithium ion batteries are, the lithium ion is the actual charge carrier. It's not the anode or cathode. And lithium ion batteries are typically rechargeable. That's the reason people use lithium ion, is because it's a rechargeable battery technology. And it's become I say that and then I notice this calls it a rechargeable lithium battery. I just noticed that. This would be a lithium ion battery. So the difference between, generally if people say lithium battery or if people say lithium ion battery, is lithium batteries typically refer to lithium anode. Lithium ion typically refers to rechargeable batteries that use lithium as the charge carrier. Battery capacity is an important topic. A lot of times, with traditional alkaline batteries, a lot of times you won't see this. A lot of times it's not shown. A lot of times it's not as relevant. It's kind of just a standard. If you're buying a AA or AAA, it is what it is. It's sort of a standard capacity. That's not fully true. There's a lot of new battery technologies, especially these like eco-friendly batteries, these carbon batteries. You'll see these. A lot of these batteries might be in a AA or AAA form factor, but they have much lower capacity than a normal alkaline battery. So it is something to pay attention to. Battery capacity is just a measure of how much energy a battery can store, which we normally would just say in joules. If you ask, how much energy can this battery store? You would guess, well, you'd probably give it in a measure of joules. That's not the case, typically, with batteries. So batteries, you typically use either amp hour or milliamp hour as a reference to the battery capacity. And a couple of things to note: the amperes times hours is not a unit of energy. So what's missing in this rating is the cell voltage. So the cell voltage is the parameter that's missing. If you want to know energy in joules, that's going to be cell voltage times amps times seconds. So basically, if you took amp hour and multiplied, how many seconds are there in an hour? 3,600. So if you took amp hour, multiplied it by 3,600, then you would get the number of amp seconds. And if you multiplied that by the cell voltage of the battery, that would tell you the energy in joules of the battery. So why don't we just say energy in joules? Well, because giving the energy in terms of milliamp hours or amp hours is often a more useful way to think about the capacity of the battery. For instance, looking at these AAAs, these AAAs have a capacity of 800 milliamp hours, which tells you immediately these could provide 800 milliamps for 1 hour, or they could provide 1 milliamp for 800 hours, right? I mean, there's lots of ways you can think about it, but it's very easy from that rating to identify how much current will this battery be able to provide and for how long. Same here, 2,300 milliamp hours. Well, if I'm consuming 10 milliamps, it's going to last for 230 hours, right? It's very easy to quickly do these sorts of calculations. And then, there is still that issue of the cell voltage, which does matter in terms of overall energy. But usually if you're using a certain battery for a certain application, the system voltage is not necessarily as much of an issue that you deal with as the current. So typically it'll be everything's operating with some fixed voltage. There may be, could be the voltage could be converted using a buck or boost, in which case you maybe would have to do a little sort of current and supply voltage swapping. But if it's a linear regulator, then it's easy. Current in equals current out. So it's much more straightforward. So battery capacity typically given in this amp hour, milliamp hour rating, not ideal. I mean, not ideal from a pure SI units type standpoint, but it's very useful. It's a very useful measure. It's easy to do back in the envelope calculations. Should be noted, right? These are D batteries. If you were like me and you grew up in the 80s, people would, walk around with boom boxes that had about 12 of these suckers in them, and they would go bad after a couple days. We spent a lot of money on D batteries in the 80s. It was a heyday for battery tech. But there's a big difference between a D battery and a AA. A D battery is typically 10,000 to 12,000 milliamp hours. This is a rechargeable one, I believe, shown here, because it's the only rechargeable ones are often the only ones that tell you the milliamp hour rating, because that's where it's really relevant. But a normal alkaline D battery is going to be 14,000 to 10,000 milliamp hours. So that's a fair amount. That's a single D battery could provide 10 amps of current for an hour. I mean, that's impressive. So or 14 amps of current, even some of them can. So yeah. Let's do an example. So you're charging a 950 milliamp hour LiPo battery using the maximum charge current of a standard USB connection that's 500 milliamps. How long will it take to charge the battery? Well, so the battery is 950 milliamps times hours divided by 500 milliamps gives you, I should have just made it 1,000, made the math easy. $1.9 hours. 114 minutes. Let's do another example. This one is much more complicated. You are using an 800 milliamp hour AAA battery to power a circuit that boosts the 1.2 volt battery to 3.3 volts, and then powers a microcontroller with a wireless transmitter that consumes an average of 12 milliamps of current. Assuming 100% efficiency, how long will your battery last? I want to go through this problem. I want to answer this problem two different ways. First of all, let's just do it straight energy. Let's just do a straight energy assessment here, because they say 100% efficiency. So just doing straight energy, what's the energy capacity of the battery? Well, if we're doing energy capacity, we actually, like I said, it has to be cell voltage times the milliamp hour ratings, times the conversion from hours to seconds. So for a AAA battery, let's do this one first. So this is going to be so it said, we've already said it's 1.2 volts. So 1.2 volts times 0.8 amps times 0.8 amp hours. So that's 0.8 times 3,600. So that's 3,456 joules. So that's the energy in this AAA battery. How much energy is that? There's lots of ways to think about joules. My physics teacher in high school used to refer to a joule as about the energy it takes to lift a Big Mac or lift a quarter pounder, like up off a table or something. I don't know. He had some explanation. For me, I like guns, so I usually refer to them always in terms of gun energy. So this is a rifle round, 34. This is a powerful rifle round. So that's, one AAA, about the stored energy of a rifle round. So a big rifle round. Which is, I don't know, kind of a lot if you think, well, is it a lot? I don't know. No. It's enough to lift 3,456 quarter pounders with cheese off the ground. How about that? We can lift 3,000 quarter pounders off the ground. Okay. All right. So that's our energy that the battery can provide. Now let's look at the other end of it, and we can say, what's the power dissipated by our circuit? So if we know the total energy and we know the power consumed by the circuit, the time span, the how long, is a simple matter of taking the energy and dividing it by the power, and that should give us the total time that the battery will last. So let's find the power now for the circuit. Our circuit was 3.3 volts, and it consumed 12 milliamps of current. So the power for that circuit is going to be 3.3 times 0.012. And that's going to be so that's going to be 39.6 milliwatts, 0.03 or 0.0396 watts. So now we can just do a simple division. We can do So the time this is going to last is going to be the total energy, which is 3,456 divided by the power, which is 0.0396 watts. So I get 87,272 seconds. So divide that by, if we want to know something a little more useful, I don't know how much 82,000 or 87,000 seconds is. That doesn't have much meaning to me. So dividing it, 24.24 hours. All right, it's going to last a day. So off this one AAA, this circuit's going to last a day. That's kind of cool. Let's do it another way. So we found remember that 24.24.24.2, 24 hours. Let's do this another way. Let's do this a current way. And doing this the current way is also going to let us kind of talk a little more about boost regulators. Maybe I should have used a second slide here. Okay, so the input to this boost regulator, we have 1.2 volts input to this boost regulator. And the output is going to be 3.3 volts. Oh, geez. What is going on? The output's going to be 3.3 volts at 12 milliamps. Now, with boost regulators, if you have a high voltage input and a low voltage output, you're going to have a low current input, a high current output. But to quantify that, if we say this is 100% efficiency, the power in is going to be the power out. And so what's the power out? The power out here is going to be 3.3 times 0.012. So the power out here, power out being voltage times current, is going to be 3.3. We already did this, so it's going to be 39.6 milliwatts. With 100% efficiency now, we can just easily, directly calculate what the input current is going to be. Because we know that on the input, on the input, we know 1.2 volts times the input current is going to have to equal 39.6 milliwatts. Now, a lot of students might be saying, you never taught us this. Where do you get these equations from? This is basic physics. So this is drawing back from your prerequisites. So hopefully, if you don't remember the energy power conversion stuff, just go back and refresh your memory. But it's assumed in this class that you've taken physics, that you know about power and energy and time and work and all that sort of stuff. So to find this input current, just divide by 1.2. The input current is going to be 33 milliamps. Okay. And we know that we had an 800 milliamp hour AAA battery. So to find the time, to find out how long this battery is going to last, we can simply do 800 milliamp hours divided by 33 milliamps. That gives us 24.24. So two ways to do it. So two ways to do these sorts of problems. One of them is just raw energy. The other way is sort of just by doing current, by sort of saying, based on our output and based on the type of converter and the voltage change and the efficiency, how much input current do we, how much current from the battery do we have? And then once you know the current, that's really when the milliamp hour rating of a battery is very useful. So, but ultimately we kind of did the same math. We just approached it from two different directions. So hopefully this example, doing this problem from two different directions, helped you pick your favorite, or helps you be able to answer these sort of questions on the homework or the final. There's going to be one kind of like this on the final. Just heads up. That's what you get for watching the video. All right, now C rating. This is, I should have made this C ratings. I love when I find little errors on my slides. Cratings. This is a section on cratings here. So once again, just like with capacity, we use this weird measure of capacity of milliamp hours and amp hours. And when it comes to maximum charge and discharge current, we also do something weird. We do C ratings, right? So we could have just defined the maximum input and output power. We could have maximum input and output. We could have used power. We could have used watts. We could have used current in, current out. Instead, we use C ratings. So a C rating for a battery tells you, it's a way of defining the maximum input and output power of the battery. However, it's again done to be as useful as possible. It's to let people make a back of the envelope calculation. So you can look at this number and you can immediately tell in very useful terms how quickly you can charge and discharge this battery. A C rating, it relies on the previous capacity rating we talked about of amp hours and milliamp hours. And it tells you what multiple or what fraction of that current rating, of that capacity rated current, you can have at the input or the output of the battery. And none of that I just said made any sense until we do an example. So if we have a 1500 milliamp hour battery and it has a discharge rate of 2C, that means it can discharge at 2 times the current rating of the battery, which is 15, I shouldn't say current rating. It's 2 times the capacity rating of the battery, which is already weird. It's already weird to use this. How many milliamps in 1 hour can we provide? But it's saying basically whatever that number is, that times 2 is the maximum input. So in this case, a 1500 milliamp hour battery with a discharge rate of 2C would be 2 times 1500 milliamps, which would be 3 amps of discharge. So basically the maximum current the battery could output would be 3 amps here. Same thing happens on the input, on the charge rating. Most batteries cannot charge as quickly as they can discharge safely. So normally the charge rating is going to be much slower than the discharge rating. And so let's do an example. A 650 milliamp hour battery with a 0.5C charge rating could have a maximum safe charge current of 0.5 times 6,500 milliamps equals 325 milliamps. So basically you couldn't charge this faster. You couldn't have more than 325 milliamps of charge current flowing into your battery. And this goes back to when we talked about with the project, when we talked about the charge controller, there was a resistor that we could program, that we could choose to set the charge current. This is where that matters. The battery if the battery that you chose had a 0.25C charge rating and it had an 800 milliamp capacity, you'd have to do 0.2 times 800 milliamps to tell you the maximum current you should ever have flowing into that battery. And that would allow you to design what resistor value do I need to set the current limit with that charge controller. What you don't want to do is just always use, a lot of students think, hey, it's a 500 milliamp hour charge controller. Why would I want to go slower? Let's just do the full dose of the stars, 500 milliamps, go for it. Let's get that battery charged up quick. The problem is that'll damage the battery if the battery can't handle it. So sometimes the battery might be okay with that, but you have to do it. You have to check. You have to check the C rating, see if that's going to work. So one nice thing about the C rating, if there is a nice thing about this C rating as a weird way of sort of telling how much current can go into or out of a battery, is it very quickly tells you how quickly the battery can be charged or how quickly the battery can be fully discharged. Because the capacity rating was, the amount of current that can go for 1 hour, the C rating tells you what fraction of an hour the battery can charge and discharge in. So for instance, a battery that is rated to 20C discharge will take 1/20th of an hour, which is 3 minutes, to fully discharge. So at a maximum discharge rate, a 20C battery will always take 1/20th of an hour to discharge. Similarly, you can look at the charge rate the same way. It's almost more useful in the charge rate, because if you get a battery that has a charge rate of 2C, that's really good. That means you could charge that battery in a half hour or, close to it. There's stuff at the end that has to slow it down, but you could get it mostly charged in half an hour. Another example, if you have a battery with a 0.25C charge rate, it will take a minimum of 1 divided by 0.25 equals 4 hours. Minimum 4 hours to charge this battery. So important terms. And you'll see this if you're shopping. So I just went to Hobby King, did a screenshot of their battery section, and you'll see this, that you have these 25C LiPo, 75C battery pack. Holy smokes. So 75C battery pack, that's good. That could dump the entire battery pack in less than 1 minute. Oh man. Holy moly, that is like a rifle right there. LiPos are scary. You got to be really careful because think about that. 1300 milliamp hour battery at a 75C discharge rate. Let's do some quick math. I did not see this till I just am now looking at this. I didn't know what I screenshot. I knew there was stuff on there. So I should check that closer. Could have. Yeah. Yeah. So this battery can output 97.3 amps of current. 97 amps of current, and it's a 4S battery. So a 4S battery, that means there's four cells in series. So that's going to be, nominally 3.7 times 4. Oops. Shoot. So that's 14.8 volts at 97.5 amps. Oof. So this thing that's 1400 watts. This battery, that's a welder. That's literally a welder. This battery is a welder that you would buy. Like, it's the same current. You could literally just take this battery and weld. I've always wondered about this. I've always thought, this battery is $24, and it is literally a welder. It's like it's a welder. And then there's this huge issue with welding where if you're trying to weld in a normal household, you don't have outlets that, you don't have a lot of outlets that can do welding. But these batteries are set up for it, right? They're like, you wouldn't need an AC. Like, I feel like in a couple of years, you're going to be able to buy a pocket welder. It's going to be, and you're going to get 2 minutes of welding time before you have to charge it. But it'll do it. It'll weld. It'll portably. I feel like I should make this. Maybe it's probably already been done. But I mean, you could literally take this battery and just weld with it, like right now. Like, no. Don't go off and make money doing pocket welders, John. You'll get sued and you'll lose everything. Stick with your safe job of being a professor. Stick with where you get to work with students. You get to teach the next generation. They get to make welders and get sued. and then probably point to this video in court and say, oh, look, this was my professor's fault, so sue him. Joke's on you. I don't have any liquid assets. All my money is in guns, so I don't have any cash for you to take. As soon as I get money, I spend it. You know me. I travel to Bora Bora. That's not true. Okay. Yeah, that's it for this 75C. Woo, this was exciting. You never know what you're going to find with me. I make these slides, and then it's a surprise. It's as much of a surprise for me as it is for you. We go from one slide to the next, and all right, what a way to end it. What a good last lecture here. This is great. All right, so battery charging. So we already talked about these a little bit when we did the project. We kind of jumped into talking about these just enough to be able to design our charge controller. And the main thing to note is that every battery, it's not only about there's a maximum current that can flow into the battery, there's also a maximum charge voltage. If you overcharge a battery and exceed the maximum voltage, it's going to start to destroy itself. And so remember that matrix that the lithium ions are trapped in, at a certain point, you will start to destroy things. You'll start to oxidize things, and you'll start to permanently break your battery. But having a voltage limit and a current limit means that charging has to go through a process. The process starts when a battery is discharged. It starts with a constant current mode. So it starts at a time when the battery current is constant until the voltage of the battery reaches some threshold, at which point it switches to a constant voltage mode, where the voltage stays the same and then the charge current drops. And then you get to a certain point in time where if at the maximum voltage of the battery, your current drops to a certain low level, that's the point where you say, okay, we're done. The battery is full. This will technically, go on for forever. At a certain point in time, you say, all right, that counts. That counts as full. There's usually a couple different things you can do once you hit this point too. One thing you can do is some battery chargers, when they detect that the battery is charged, they just do a constant trickle charge. They maintain a constant voltage. So some of them will just hold, some of them will literally just let this exponential go on forever. Some of them will switch to a constant current, where they will just slowly trickle current into the battery. Sometimes they will even do that to the point where they will allow the voltage to actually even go up a little bit. And what they're saying, I know when this battery is full, that if I just keep putting 5 milliamps into it, that's not enough to actually damage the battery. Or whatever, if I put some small constant current, that's enough to keep it fully charged and it won't actually damage it. So I'm just going to keep this little trickle of current flowing in to keep it all topped off. That's less common with LiPo. LiPos don't really like that much. So, but you'll see that a lot with like lead acid batteries where they're like, "Yeah, I can handle it. Just as long as you only have half an amp of current, that battery can take a half an amp even when it's full all day long. So it'll make a little gas or whatever, but don't do that." But I mean, there's people get different battery technologies have different levels of robustness. So lithium polymers typically don't like to be overcharged. They don't like to be undercharged either. The other option is you can completely cut out. So you can say, once the charger realizes this battery is charged, it'll say, I'm done. No current, no voltage until this battery gets used and until it gets down to a certain level where I need to start saying, it'll wait until it gets down to, about here again before it starts a charge cycle up again. Different chargers have different levels of intelligence on that. Some chargers also have this pre-charge range. So if you hook a battery up to a charger and that battery is like dead, like way dead, like way more dead than it should be, you generally don't want to over discharge these batteries. But if you do, some more intelligent battery chargers know this is bad. This is not good that you let the battery drop all the way down. So as we charge it back up, as we get it back to this sort of bare minimum operating voltage, we're going to do it slowly. So some of them will have this pre-charge current, where they do a pre-charge at a low current until the battery gets up to the point where now it's actually up to a level of charge where it's sort of the minimum that you should discharge the battery to. Once we get up to that, then we go back to the normal charging mode. So some of them do this pre-charge, and this is meant to prolong the life of the battery. So it's meant to minimize the damage you do to the battery when somebody did over discharge the battery. Practical ICs, you've already looked at one. We did a very simple version of one, so I'm showing a more complex version of one now. So the project used one. The project used a low current charger. And one thing to note is the maximum voltage is typically set by the manufacturer. So you can buy these chargers that are set to max out at 4.1 volts, to max out at 4.15 volts, to max out at 4.2, 4.25, 4.3. There's a range of different maximum voltages that you can buy that they'll go to. And again, it's a matter of knowing your battery, knowing your particular battery chemistry, and knowing your design. Some designs, they say, this thing is never going to be recharged. It's not going to be recharged 1,000 times. We don't have to worry that much about the battery. But what we do want is we want to get as much power or much energy out of the batteries as we can. Let's bump it up to 4.3 volts. Some of them say, nah, we want to be careful with this battery. We want to get as much lifespan as we can. Let's only charge it to 4.15 volts or something like that. So, and again, this is where I'm not an expert on why you would do one or the other. I'm just saying people do it, and you can buy different versions. But it's usually for the cheap ones, that max voltage is set at the factory. And charge current is usually kind of the only thing you get to control, and that's usually you can control it with a resistor value. And the charge profile, which we talked about earlier, is also normally just predefined. So more advanced regulators, quite often these regulators have a more advanced digital controller. You can usually program them using some sort of communication protocol. In this case, I think is a TI charger. And it allows a host microcontroller to communicate with it over I2C, and it lets you program a bunch of different parameters. So if we go back to here, it lets you program this, it lets you program this, it lets you program this, right? So a lot of these things you can. I don't know if this particular version of the battery actually lets you do all of these, but these are the types of things that you can normally do with programmable charge controllers, or with digitally programmable. Choosing a resistor value is a programmable charge controller, but digitally programmable, these are the types of things you can control. Also, a lot of these charge controllers will have a bunch of goodies on them. So this charge controller, one of the most important things to note is this one, the battery is connected up here. The battery's connected up here, and what's this? That's an NTC thermistor. So that's something that the charge controller, if your battery starts to get too hot, it says, pump the brakes a little bit. Let's slow this thing down. Let's not destroy the battery. But you'll notice that the system load and the battery are not the same thing. In our project, what did we do? We just had the charge controller going to the battery and the battery going directly to the boost converter. That creates, for a lot of systems, a problem. And the problem is, if you're an intelligent battery controller and you have current going to your battery, if there's a load on the battery, if there's something pulling current away from the battery, you don't know that. And you don't have a way of isolating the load from the battery. When you charge a battery, what you want to be able to do is fully isolate the load. So you want to be able to pluck the battery out of the circuit, charge it, because when you do that, you know that any current I send to the battery is actually going to charge the battery. I know what I'm doing to this battery. If a load is connected to it, I don't know how, if you're the battery charge controller, you don't know how much current the load is drawing. You don't really know what you're doing. But something like this, where we isolate, where the battery is isolated from the load, and inside here, right, inside here, there is a gate. And so this system can intelligently, if it knows I don't have enough current coming in to power the load here, it'll turn on that gate and it'll say, all right, I'm going to let the battery give some current to the output load because I don't have enough, while I'm charging, I don't have enough input current to handle what the load is trying to draw. So whatever. But that's an important thing to note. Sometimes you need to do load isolation. So it's easy enough to do. You can generally just do it with 2 transistors. So the idea is while you're charging, you generally want the input charger to power the load directly, and you also want the input charger to power to charge the battery. And the only issue is, again, if the load starts to draw more current than the input charger can provide, then generally either everything's going to shut down, or you need to actually have, while the battery's charging, you need to occasionally have the battery actually provide current as well. This happens with laptops a lot. A lot of times you'll find if you have a laptop and it has like a wimpy little 45-watt charger, you might notice if your laptop's doing a lot of heavy lifting that your battery starts to drain while it's plugged in occasionally. And that's sometimes just because if you have a 45-watt charger and your laptop's consuming more than 45 watts, then it's going to have to use the battery. And instead of, or another thing you'll notice is if your laptop's plugged in and it's doing a lot of stuff, sometimes it will take an eternity to charge up. And again, same thing. If you have a 45-watt charger and your laptop's consuming 30 watts, well, then you only have 15 watts available to actually go to charge the battery. Okay, all good things to keep in mind. This one also provides a little regulator, so extra little goodie. So it has a built-in, this charge controller also has a little built-in, looks like a linear regulator. And that can be handy to, just to save yourself. And sometimes manufacturers put these in there just so that if you're considering buying this thing and you say, this costs $1, come on, TI, I don't want to spend $1 on this. What are you doing to me? TI says, hey, I included a free linear regulator in that thing for you. So watch yourself. You'll be grateful for that. It changes your design design decisions. So anyway, so look for goodies. Look for goodies in these charge regulators. Look at cost. If you're actually designing one of these for a product, it's going to be based on what the product's needs are. Some products, the most important thing is keeping it cheap, in which case this probably isn't the charge controller for you. Some of them they need to have high current or fast charge times. Maybe that is right then. I don't know. There's lots of these design considerations you need to take into account though. So, but load isolation is what we're talking about here, where the charge controller has separate isolated connections to the battery and to the load. And that means the charge controller usually takes care of the switching as needed. Multiple cells. So far we've kind of glossed over this notion that the standard lithium technology batteries are anywhere between 3.3 and 4.5 volts per cell. So the lithium, a lithium ion has like an ionization energy of like 5 volts or something, but for practical reasons, the most you can usually extract is like 4.5 volts or so. I don't know. Again, I'm not a chemist, but yeah, typically these lithium-based batteries per cell, you're gonna get 3 to 4.5 volts out of them. And a lot of times you want a battery with a higher battery voltage than that. So, quite often, if you don't want to have to use a boost converter, boost converters can have their own issues. They're noisy, they're expensive, they're not necessarily super efficient. If you want to have a high voltage and a lot of current, you might just need a whole bunch of cells stacked up. And you can do that. So if you had you know. So in here, right, you'd have 12 volts, or yeah, about 12 volts here. And there's some issues with this though. The problem with connecting lithium-based batteries in series is when they're connected in series, there's this all the same current flowing through all these batteries, right? This current I. And that wouldn't normally be a problem except for the fact that it is possible that not all of these batteries are charged to the same level. So if, for instance, looking at this battery, right, this battery is a little more discharged than the others. So if this battery, for whatever reason, becomes a little more discharged than the other batteries, it's still going to have current extracted from it at exactly, it's not like the weak battery is just uses less current. The current flowing through one battery is the same as the current flowing through all the others. So what's going to happen is as this battery, a battery is technically a collection of cells. Sometimes we use the term battery to refer to a single cell. Technically, the term battery refers to a collection of cells. So this would be a cell and this would be a battery. But as this battery then discharges, this one little weak cell in the middle is going to be completely depleted before the others. So these two will still have energy, whereas this middle one will be completely depleted. Now, here's the thing. You can either detect that happened. So, eventually once this thing gets fully depleted, this voltage here is going to basically be 0 volts, or it shouldn't be 0, but it's going to drop a lot. And a lot of systems will detect that. They'll say, yeah, my battery voltage just dropped from 12 volts down to 11. This thing is dead. We got to turn off. Some of them won't. And the problem is if they don't detect that, if they do detect that, it's still bad because you wasted all this energy. You had all this stored energy that you don't get to use. Your weakest link is what defines your lifespan. But the bigger problem is if you keep running this battery, you will actually you will reverse charge this battery. It'll be fully discharged, and these other batteries will keep forcing current to flow through it, and that destroys a battery. That really destroys a battery. And so this creates a need for whenever we're using lithium batteries and we have them connected in series, we need to make sure they are balanced. So we always need to make sure we do some kind of balancing on these batteries. Balancing is a way of maintaining the same level of charge, or usually it's maintaining the same level of voltage across every single battery in a series collection of batteries. And there's a couple ways to do this, but let me go back a little bit here. So one thing you can do is a lot of these devices that do cell balancing only balance the cells at the point of charge. So a lot of times they will only, when they're charging the batteries up, that's the only time they'll make sure they're balanced. So when they discharge, you hope if you charge them all to balance that they'll discharge at about the same rate, but it's still something you have to be careful with. What causes this imbalance? So a lot of students just say, well, they're all the same cell in series. Can't we just assume they all are going to behave the same? You cannot, because a lot of what causes these imbalances is self-discharge. So tiny little microscopic, angstrom level defects in a battery can cause internal current flow. Internal current flow in a battery can cause a battery to discharge itself, and each cell is going to discharge at a different rate. Again, we're talking about microscopic imperfections in batteries that vary in the manufacturing process. So if one battery has a self-discharge rate of 100 microamps and the other batteries have a self-discharge rate of 20 microamps, well, if you wait a couple months, one of those batteries is going to be way more discharged than the others, and then you're going to run into this issue. So it's preferable to always be balanced, to always keep these cells balanced at all times. It's the best way to avoid damaging the battery. That's the best way to avoid inefficiencies due to one cell discharging and the others still having energy stored in them. So how would we actually charge this? So one issue is, what we'd like to be able to do is just apply a big voltage here, right? We just like to apply a voltage here, whatever. And charge all these batteries up at the same time. But as we mentioned, if you do this, right, let's say you can maybe do this once. You charge this up once. One of the batteries is one One of the batteries had a slightly higher self-discharge rate. So after you fully charge the battery, one of the cells wasn't quite fully charged and the others were a little bit overcharged. But then over time, it gets worse. Over time, that one cell that had a higher self-discharge rate, it's going to drain itself faster. And then the next time you charge it up, it's going to be even more imbalanced. And so on and so forth. And eventually it will destroy the pack. So if you want to balance as you're charging, you need to have access to these intermediate connections in this battery pack. You don't necessarily need a lot, but you do need a connection here. And that is what, if you ever look at these lithium battery packs, like you'll quite often see something like this, where you'll see a little plug with just these little, these aren't like huge, these aren't high gauge wire, right? These are some fat wires here. This is just kind of a, little thin wires. And what those wires are doing is those are giving you access to these intermediate terminals of the battery. And then how would you charge this? Well, one way you could charge this battery is just do this. Just apply a big giant voltage here. So let's just apply what is 3.7 times 4. That's going to be 12, 40, 14.8 maybe ish. Well, let's do 4.2. 4.2 times 4, 8.4, 16.8. So you're applying 16.8 volts here, but then you're measuring these voltages here. And if, let's say when you measure these voltages here, this one you're getting 4.1, well, let's say we're doing constant current and we're down a little bit. We're just 16 volts, right? So this one you're getting 4.1, this one you're getting 4.1, this one you're getting 3.8, this one you're getting 4. So one thing you could do, usually the way these balanced chargers work is they just have a little burn resistor. So they just have a transistor and a burn resistor, and whatever the highest cell in the battery is, they just discharge it. So in this case, you could just, on these two, you could just burn current through here and discharge just that cell, just these two cells, until after you discharge it, and you'd probably also discharge this one a little bit too. And then after a while, right? And then you keep charging. Now, and this is, this is not really how these work. It's not, you never get this far out of whack. If you have a balanced charger, it's going to constantly be, it's going to constantly say, if any of the cells are even a slightest bit running away from the others, it'll fix it. It'll fix it on the fly. More efficient chargers will actually, instead of just burning the voltage across the cell, they'll use it. They'll take that energy. They'll take that energy that the cell has, and they will use it to charge other cells. So they'll use it. So basically, they'll charge the weakest cell with the strongest cell, and keep doing this until and everything will stay nice and balanced. You don't have to charge these batteries also by just applying 16 volts. So one thing you can do is you can have a single cell charger, and you can have that single cell connected to each battery. So each battery can have its own little single cell. Now you might notice though, the problem is this terminal and this terminal, neither of them are ground. So if you're going to charge the cells this way, if you're going to charge them cell by cell, you need to have a isolation. So you need to have the circuit that powers these single cell chargers needs to have an isolation. It needs to be an isolated supply, The other thing you can do is have one. So you can have one single cell charger, and you can just have a bunch of switches. So So you can have a bunch of switches on these. You know, you get the idea, right? So basically you close the proper switches. So you charge one cell for a little bit, and then you jump over the next cell and charge it for a little bit and jump over the next cell. And so this means you only have to have one isolated charge circuit. You only have to have one isolated circuit. But it's just going to keep switching, and it's going to charge each cell and for a fraction of a second and just kind of keep going along these cells. And as it does it, it's going to keep it balanced, right? If it notices one cell is a little slightly lower voltage, it's going to charge it for a little bit longer, then it's going to move on to the next, and it's going to keep doing this. The flip side there, though, is, you know, your charger has to be, in this case, if you wanted to charge this entire battery at an average of 1 amp, you'd have to have 4 amps of charging capacity per cell. And you'd charge one cell at 4 amps for a few milliseconds, and then you charge the next cell at 4 amps and the next one, and that would be equivalent to charging the entire pack with 1 amp. So something to keep in mind. But this is the idea. When you're dealing with multiple cells, you either have to have multiple single cell regulators, a regulator or a charger that can provide a big voltage of the whole thing and then connect to these little intermediate signals and keep everything nice and balanced, or you have one charger that's sort of switching between each one of these separate cells very quickly, keeping everything balanced as it charges along the way. And again, there's design trade-offs to all of these, but you should know that this is what you have to do. Charging multiple cells with lithium-ion technology, you have to manage this imbalance issue. You have to manage the self-discharge and imbalance issue. So, other considerations. So a lot of times, if you're a battery manufacturer, you say, I don't know what kind of crazy thing people are going to do with my battery. I don't know what they're going to hook it up to, but I do know that my battery can really hurt people if it goes bad. Lithium batteries are notorious for catching fire. You see videos every year, you see videos of people, they had an e-cigarette inside their pocket, and it had a lithium polymer battery, and something went wrong, and that lithium polymer battery caught fire. And then you see these videos of people sort of swatting at their pocket as their pants catch on fire, and they're kind of funny, but I mean, that's not funny, haha. Well, it's kind of funny, haha, but in a dark way, in like a step on a rake, somebody got injured, but I don't know why that's funny. Maybe it's not. Maybe, it's the last video. Yeah, I can't get fired. I don't know. You know what I mean, right? You see these videos of people and their LiPo batteries went bad. They're notorious for this. Airlines do not allow you to take lithium batteries on planes anymore because they do this. They have this funny thing they do where they just catch fire and they burn people's pants and stuff like that. So a lot of times battery manufacturers or people who are taking the battery cells and packaging them for use will incorporate circuitry on the battery itself that protects the battery. So if you ever see one of these batteries and it's got a little circuit board in here, normally what that is what's called under voltage lockout and over voltage protection. So if this circuit detects the voltage in the battery ever gets too high, it's going to disconnect the battery, or it's going to burn the voltage. If it detects the voltage in the battery gets too low, where you're over discharging the battery, it will lock out the battery. It will separate the battery from the rest of the system until it gets charged back up again. So quite often you'll see this. You'll see protection of the battery done at the point of the battery rather than at the point of the circuit. And this is a design, as an engineer, this is a design decision you can make. You can either, if you don't know that your battery will be safe for operation, you can either design over voltage protection and under voltage lockout on the circuit board, or you can punt and say, hey, I'm just going to buy a battery that's got this built into it and not worry about it. And then I'll let my circuit die. I'll let my circuit just burn. I won't ever monitor the battery voltage. I'll let it burn until it shuts itself off. Right? It's a design decision. They swell. If you ever see a LiPo battery that has its pack is swollen, don't use it. It usually means it's gone bad. If it's swollen a lot, if it has a little bit of wrinkle to it, yeah, it might be okay. If it ever looks like that in the picture, just throw that thing away. These packs that these are in are designed to keep them as safe as possible. So they're packaged in these little metal foil, mylar, whatever, little baggies. And that baggie is supposed to keep it so that if it does catch fire, it catches fire inside the baggie rather than outside the baggie, which this is a fire outside the baggie. And this is one of those videos where somebody probably just stabbed it with somebody took a a nail and ran it through it, and just to show you what happens when these catch fire. But they can release a lot of energy very quickly. So again, these batteries have the energy of, like, even a AAA has kind of the energy of a rifle round. So there's a lot of energy in these batteries that can be released from the battery very quickly. So hey, we ended it on fire. I believe we ended it. Yep, we ended it with fire. So it's been a pleasure. EE320. We're gonna call it quits here. Enjoy the flames. Hopefully your project, avoid the flames with your project, but know that they can happen. So as an engineer, you always have to be very careful. There's other things that we didn't mention in this video. So one of the biggest things I want to just quickly talk about is, one of the things that especially you'll deal with your senior project is there's quite often ethical considerations for technologies that you should take into consideration. If you work for a company, quite often the engineers are a little bit isolated from other decision makers in the company, to the extent that other people don't always know what the engineers do, and the engineers don't always know what they do. And engineering as a profession means you have expertise that sometimes other people don't understand. And so if they say, hey, pick a battery for this design, you'll say, all right, I want a lithium battery. They'll just say, okay, they picked it. But sometimes that means that there are ethical considerations, there are environmental considerations that aren't taken into account. So to the extent that engineers nowadays should be familiar with some of these ethical concerns. This class doesn't go over that. It's beyond the scope of this class, but it is something that is important, and it is something that we will talk about later in our curriculum. And it's really easy as an engineer to think, well, to not realize the scope of what you're doing. If you're designing a consumer electronics product, there might be 1 million of those produced. So you might say one lithium battery, well, who cares? But times 1 million, and now small design decisions can have big overall consequences. So taking into account the broader impact of designs, ethical considerations is important. We don't talk about it. We do talk about flames. We talk about fire. All right, everybody. Thanks for watching the series. And I will see if you are in this class. I will see you for your senior project. So the next time you'll see me, oddly enough, we'll be doing very similar things. We'll be doing DC to DC converters and microcontrollers and Altium. So it's gonna be a lot of me for these topics, and I'll see you when you're seniors. So thanks for watching. Thanks for a great quarter. I will see you all on the flip side.